ICTS and thank the organizers for giving me this chance to come over. So this is probably the first opportunity for me to speak in front of the StatPhys community of our country. So I'll go straight away to the topic. I'll be talking about universality of another kind. Basically, my interest is in heat engines and their efficiency. You may say that this is a very old topic, a textbook kind of problem. But of course, the dynamics of the heat engines and their thermodynamics is of current interest also, and we are always trying to improve the efficiency of our engines. So I will try to compare that thing also. So let us start with a very standard result, the basic theorem in thermodynamics, which is the Carnot theorem. It tells us that the maximum efficiency which a two reservoir setup can have is this value. When we say reservoir, they are infinite in size so that their temperatures are always constant, however amount of heat you extract or give it to them. So this is basically quite well known. So what we are trying to do is that you try to model the reservoirs not as infinite systems, but systems which are finite, having a finite heat capacity and so on. So what I will assume is that both the reservoirs, the source and the sink, they follow the same fundamental relation. So basically the only difference between them is in the temperatures and the consequent entropies of the systems. This will be the source at a higher temperature. This is the sink at the lower temperature. So we want to use them, use a temperature gradient between them to extract work. And so the maximum work which can be extracted is given by thermodynamics. It says that for a reversible process, you can extract the maximum work. So the reversible process means that at any time, the entropies of these two systems, the sum of the entropy, it stays constant. But what happens is that when you extract heat from this system, its temperature drops, and when you dump heat into this, its temperature rises. So when the final temperatures, they become equal, then the process stops. So in this, we can see that because they are the same system, so the entropy of each system at the end of the process is this. And so you can calculate the work, which is just the difference of initial and final energies. And this is the heat which is extracted from the hot system. So this is the definition of the efficiency. So just by looking at the formula, you can see that this depends on the nature of the system. So whatever form of the function you take, it decides how the efficiency will look like. So in the past, people have done work on this, assuming simple kind of systems where you can assume a constant heat capacity or some simple forms. But it is clear that the general formula, it depends on the form of the U. So what we are asking is there a kind of universality? So when I say universality, it means that the expression for the efficiency is independent of the form of the function U, and it only depends on the initial temperatures. And it will be nice if it depends only on the ratio of the temperature, as in the Carnot efficiency. So to do the analysis near equilibrium, I use the linear response theory. And the terms which I have, U S minus, or the minimum energy, I expand around this point where delta S is the difference of entropy. Similarly, I also need to expand this function. So I do the analysis up till the second order. What we find is that if you apply this linear response theorem, then the efficiency is basically of this form. So this is the Carnot efficiency, which is the difference of the temperatures divided by the higher temperature. So just to show it how it looks like, this formula is slightly better than the half Carnot. So this is full Carnot, this is half. So very near equilibrium, it is just like half of Carnot. So this is the first instance of the universality that I am speaking about. Then, of course, you would like to generalize it a bit. And the simplest way to do it is that you consider the source and the sink to be of different sizes. The simplest way to do is that you keep the function same, just collect more than one copies of the same system. So you have m copies here and n copies here, right? So m and n can be any numbers, whichever you like. So now this is my source, which is at a high temperature. So because all the systems are at the same temperature, so the temperature of the source is also T plus. This is T minus. And again, I apply the maximum work theorem, which is to extract work by a reversible process. So the total entropy stays constant, and the entropy of each system or the subsystem at the end of the process is SC. Then I calculate just the work with the difference of energies. And so this is the quantity of heat which is absorbed from the larger, which has m copies. So I define the efficiency. And again, if I use the expansion up to the second order, I already know how to expand this. To expand this, I use this formula basically. So this is the second derivative which is given by this. Then I get this formula. So this, of course, depends on the sizes. It is nice in the sense that it only depends on the relative sizes. It depends only on the ratio m over n, kind of, apart from the Carnot efficiency. So it reproduces very nice kind of limits that if the sink is very large compared to this, then this formula goes to this. And when source is very large, then it goes to this. So because it is going monotonically, then you can say that the efficiency for the general setting, it remains within these two bounds. So this is all done for a quasi-static process and with the different sizes of the heat and sink. So these results were reported in this publication. Okay, so this is a kind of, we think it's a new result in the sense that it reports of a universality which was not expected earlier based on these models, because you think that they may depend on the nature of the system, which is the finite reservoir. So now I will try to compare this thing or see the analogy with the finite time models. So one example of this, which is studied in literature, there are many type of models, but one type is this called low dissipation model. So it actually operates just away from the reversible limit. So what is that? That you have hot and cold reservoirs, and you have thermal contacts with them. So there are finite times for those contacts. This is the time of contact with the cold reservoir. This is the time of contact with the hot reservoir. So when these times are very large, then you are actually operating in the reversible limit. Okay. So delta S is the entropy which is produced, you can say, the total entropy generation at one of the contacts. So the sign should be different because the working medium is operating in a cycle. So whatever entropy is generated at one end, it has to be depleted at the other, so that the total delta S is 0 in the cycle. So then they define this power, because it is in finite time. This is the total cycle time for this, and you do this. So now you do an optimization over the time of contacts, right? You have two parameters, tau plus and tau minus, and you do an optimization of the power over these time periods. Then you get the maximum of power for certain values of those times, and then you can also ask what is the efficiency at that point. So this work is by these authors. So what they do is they now compare. This is the efficiency at the maximum of this function. So they also get these bounds. So these bounds are reported for a finite time model. This is the upper bound, this is the lower bound. So it happens that when the time of contact is very small, this thing, then you have a higher power, higher efficiency. When this is very small, then you get a lower efficiency. And these dots are actually the observed efficiency of real thermal power plants. They may be nuclear, steam engine, or whatever, but they are real industrial plants which are operating between certain two temperatures. So you calculate the Carnot for them and the observe use this thing. So the surprising part is that with this simple kind of thermodynamic modeling, you can find a suitable range for the observed efficiencies also. Although you have some points which are below this and some points which are above this. No, this is the maximum is this. The maximum is for this model. It is not the Carnot. It is not beyond Carnot. It's only beyond this limit, which is imposed by this model. So, but what I want to emphasize is that these are the same limits which are also reproduced in the quasi-static model. Okay. So if you see the efficiency which you obtain here, there's an analytic formula for that, and you expand it near equilibrium. You can say up to second order in the Carnot, you observe this kind of thing. And there's also you can see the up to the first order is a kind of universality. In the second order, it depends on the details of the model, which are these dissipation constants. And you can say when there is a symmetric dissipation, then this ratio is 1, and you get a factor of 1/8 to second order. So the second order term also becomes universal in that way. So we can also go beyond the linear response in our model, and then the efficiency can be written in terms of the orders of the Carnot efficiency like this. So the first order term is universal, but the second order term, it contains the effect of the relative sizes of this thing. This is the derivative of the specific heat at the hot temperature. This is the value of the specific heat. So clearly when n is equal to m, when there's a kind of symmetry of sizes, then you get a universal term of 1/8, which is also reproduced by the finite time model. So that is the main result. So what we have looked into is the kind of analogy between the finite time models and quasi-static models. They look very different. One does not involve any notion of time. Others heavily depend on the notion of time, and there's an optimization over the time which is involved. And we've also seen through efficiency that the irreversibilities which occur due to finite time, they're kind of equivalent in a sense to those you get from the finite side. Thank you.
We have time for a few questions.
Right. No, it's actually a reversible process, a quasi-static process. You extract a small amount of heat, you convert it into work, and then dump the rest of the heat to the cold reservoir. So because the working medium is operating in a cycle, so those details are not important for calculating the efficiency.
It's just an adiabatic, like
yes.
static.
Yes.
Okay, if there are no further questions, thank you very much.